the questions?
Yeah, it's like when the writing is realistic, the anti-holomorphic part was same as the bosonic.
Yeah.
But the holomorphic part has the extra term because of the supersymmetry. Right?
Yeah.
But there was one extra term which was like gamma
squared B. Yeah.
Which I don't know. I mean, I was not able to think of that term because that does not look like it's coming from some Noether transformation.
Yeah. See, the point is, this is like we have this gamma TF, right? That one we had CTM, right? This is a standard term, right? Then there is a gamma TF term, right? Which is the basically the supersymmetrization of this, right? C becomes replaced by gamma and TM is replaced by TF. Then there is a BC del C term, right? In a bosonic, yeah, and it's roughly C times the ghost energy momentum tensor, right? Because if you remember Q with B, this is the characteristic. This is Tm plus T ghost. Okay. So this other term minus 1/4 gamma square Bi, right? This is roughly the analog of gamma times the T of the ghost. Beta gamma ghost, right? TF. Yeah. So gamma times the TF of the beta gamma of the ghost system, right? Because gamma times gamma B, right? Because it's not the energy momentum tensor, it's the supercurrent, right? So supercurrent will have a product of a super ghost and a normal ghost, right? That's this gamma B. Exactly. Yeah, yeah. Exactly. So if you take UB with gamma, you will get TF, which is the usual matter current, plus TF ghost. Sorry, QB with beta. Yeah. This will have gamma. Exactly. So that's roughly the origin of this term.
Like last time, where we just wrote down the
mode expansion. Yeah, we had sum over M and N, B M minus N, something like this, right? I don't remember BCC. Yeah, so when I wrote it this way, integral JB of Z dz, right? But what you have to do, you take the expression, right? Take, for example, BC del C. Okay, so you have to substitute here, right? B. Exactly. 1 by Z minus W coefficient, those coefficients will be written in terms of the modes. Then you'll get the old expression. Writing this one. See, JB is a BRST current, right? Yeah, you first get the current and then you integrate it to get the charge, right? Because integrating over a constant circle in the radial quantization, when you go to the cylinder, it's like constant time slice.
Defining this, we don't have to care about Euclidean lorenz.
Well, no, this, when you, I don't know what you mean by you don't have to care. You can, of course, go back and forth between Euclidean and Lorentzian, right? If that's what you mean.
That when you define Noether, the procedure itself, you can forget about Z, right? You can just work with this constant time circles.
Yeah.
You can just think of it in that space, the real Lorentzian space.
Yeah.
And define the Noether charge as the integral of the zero component.
Exactly. Yeah. Yeah.
So that definition is a Lorentzian definition, is what I'm saying.
Yeah.
Now, when you Euclidenize the theory and in writing the Z variable, you have already Euclidenized it.
Yeah, true. But the point is that the integration is being done at constant tau.
Yeah.
Right? So it's inherited, you can say, from the Lorentzian prescription.
Already in the back of our head, we already have a Lorentzian section in there.
Well, constant sigma is constant sigma, either a Lorentzian or a Euclidean, right? Constant tau basically becomes constant t, right? Under analytic continuation, but the integration is always done over constant sigma. Constant t or constant tau size, integration is done over sigma, and that sigma doesn't go from Euclidean to Lorentzian, right? Sigma is always integrated from 0 to 2 pi. So you can start with the Lorentzian picture, right? Write it as an integral over sigma, and then you can analytically continue that expression. Any other question? Okay, so let me remind you that we had a mode expansion of the beta gamma system, right? So beta of z was expanded as sum over r, beta r z to the minus r minus 3 by 2, and gamma of z sum over r, gamma r z to the power minus r plus half. And these basically reflect the dimensions of beta and gamma. Beta has dimension 3/2 and gamma has dimension minus half. Now beta of 0 acting on 0 should be finite. Why? Because vacuum, right, is corresponding with the operator that creates vacuum out of the SL2 invariant vacuum is the identity operator, right? And when you bring anything close to the identity operator, you shouldn't get any singularity. Okay? So when you have an expansion like this should be finite. Okay? If you had any other state, it need not be finite because beta could have an non-zero operator product expansion, a singular operator product expansion around with that vertex operator. But with vacuum, it should be finite. Similarly, gamma of 0. Yeah, because vacuum is, of course, in the NS sector. And this implies from here that beta of r on the vacuum should be 0 for r greater than or equal to minus half. We see if r is equal to minus half, then this is z inverse, right? That coefficient should vanish. And any for r larger than this, it will be even higher powers of z inverse, so it should vanish. And this implies that gamma r acting on 0 should be 0 for r greater than or equal to 3/2. Because for r equal to 3/2, it's z inverse. This one? Because vacuum means that there's identity operator, right? Vacuum is created by putting an identity operator at the origin. And so if you put take a correlation function where there's identity at the origin and beta of z elsewhere, then as you take z to 0, you shouldn't get any singularity, right? Because beta of z identity has no singularity with any operator, right? So this follows from the fact that beta of z, I of 0, is non-singular at z equal to 0. And similarly for gamma of z, I of 0. Now this kind of thing we have seen before, right? For example, for the BC system, right? This was Bn acting on 0 equal to 0 for n greater than or equal to -1, right? Because B minus 1, B0, B1 also all annihilate the vacuum. And similarly for C, it was, I think, for R larger than or equal to 2. Okay, C1 doesn't annihilate it, but C2, C3, etc. annihilates it. Okay. But here it, yes, NS sector, yeah. So half integer model, yeah. Because vacuum, the SL2 invariant vacuum is in the NS sector, right? That we had seen already. because this is in the NS sector. But this leads to a peculiar situation, and that's because of the following reason. So this says that gamma half on the vacuum is not equal to 0. Right? Because gamma r acting on the vacuum gives you 0 only for r equal to 3/2 and higher. Because for r equal to half, you see, for r equal to half, this is finite, right? So there is no reason why gamma half acting on the vacuum should be 0. Yeah, I'll tell you what is peculiar about it. So this is analog of C1 acting on a vacuum not being 0. Right? Now, C1, let's recall what C1 was doing. C1 acting on the vacuum was giving a state with L0 equal to -1. Right? Because it will lower the L0 eigenvalue by R, right? If you have CR. So similarly, gamma half acting on a vacuum will give a state of L0 equal to -half. Right? So this has L0 equal to -half. So gamma half on 0 has L0 equal to -half. Is this clear? So far it's analogous to what happened to C. Okay? C1 acting on a vacuum gave a non-zero. But now consider gamma half to the power k acting on the vacuum. This you couldn't do for C1. C1 square was 0, right? Because C was a Grassmann, Fermionic Grassmann odd operator. This is Grassmann even operator, so gamma half square is not 0. So gamma half to the k acting on a vacuum gives you 0. This gives you, is not equal to 0 in general, and this gives you L0 equal to -k by d. And k is any integer. So this tells us that L0 is unbounded from below. Yeah? Yes.
That was the lowest L0 state.
Yeah.
But nothing else special about it.
Yeah, that was the lowest L0 state. But here, there's no lowest L0 state. Energy is unbounded from below. L0 is unbounded from below. Okay, L0 is not the physical energy, it's the worldsheet energy. Okay? So L0 is unbounded from below. Because of a Grassmann even structure, exactly. Because the gamma ghost is Grassmann even, right? This is happening precisely because of that. Well, the point is that this by itself doesn't give a serious trouble, because ultimately you have to look for cubic homology states, right? And you have to check whether we can choose representations from cubic homology which have unbounded, which have bounded energy, right?
So for some reason, there'll be some cut off K which is completely cut off by QB.
Yeah, it may happen. Okay? So then we are okay. Yeah. So true vacuum doesn't exist. True ground state doesn't exist here. Right? But it doesn't matter. You just work with the SL2 infinite vacuum and you accept the fact that there are states above and states below. No, QB gamma anti-commutator is not necessarily 0. That's a complicated object. Is this clear?
We demand that it should be 0, gamma acting. We cannot consistently demand.
No, we cannot consistently demand it, but that will be too much, because we have to demand that this for beta, right? See, beta minus of acting on 0 has to be 0, right? Because for the finiteness. If you also demand that gamma half acting on 0 is equal to 0, then there is a problem, because beta half gamma minus of anti-commutator is not 0. Right? It's 1. So if you try to apply it on the vacuum, right, you cannot both demand that gamma half acting on the vacuum is 0 and beta minus half acting on the vacuum is 0.
If we do the other, let's say, if we demand that gamma half is 0, but not the beta
Minus half.
minus 1 by half, then you wouldn't say that the energy is bounded, unbounded from below. You would say that the quantity corresponding to beta is unbounded, right? But then
No. Then what we would say is that what you are applying it on is not a vacuum, not the SL2 invariant vacuum. Then we will state like that, okay? But that state is not the SL2 invariant vacuum. Right? Because if it was an SL2 invariant vacuum, then there's an identity operator sitting there. And then beta cannot suddenly have a singularity, but there's nothing. Is this clear? Conclusion is that the spectrum constructed this way has L0 unbounded. That's only, I mean, there's a conclusion here, that's the statement, right? That's the observation, right? And we'll now leave it aside and proceed and come back to this later.
Is there a more severe problem than the C1? The fact that
Well, I mean, as I said, it's not even clear that it's a problem for string theory, right? At this stage, because for string theory, you have to look at states in the cubic homology, right?
the way you were saying it looks like it.
What? The way I said it, no. So that's to entice you, right? Doesn't mean that there is a problem. No, I mean, in string theory, there are already negative H states. It will be I k dot x, right? Can be made arbitrary negative by choosing k square to be arbitrary negative, right?
I mean, unitarity of YHGFT has nothing to.
Because it's not unitary anyway, right? Because there is a time like x0 direction. And there are ghosts, etc. So things are not unitary anyway.
I think to see that what does it mean? Means, I mean, data. Sorry, from the target space point of view.
We'll see something, right? What you will see, we'll see. See, the point is that this by itself is not a problem if you are, at least not obviously a problem if you are dealing with only cubic homology, right? Because as I said, for cubic homology, you have to see what representative you choose in cubic homology, right? If you are trying to do an off-shell theory, right, like a string field theory, then this is a problem because there you don't include only the states in cubic homology, right? The states in cubic homology are like on-shell states. Okay? Whereas a generic off-shell state will be a generic state in the Hilbert space, and there you will have a serious problem if you try to use this.
But the cubic homology now and see whether L0 is bounded there.
Well, see, cubic homology, as we had discussed, right? Any state which has an L0 non-zero can be removed. Take any state which has non-zero L0, right? That state can always be written as Q, and if it's QB invariant, it can always be written as QB on something. Okay? QB, that's from this fact that QB would be 0 is L0, right? Okay, we have to put all this C0 minus etc. But let's not worry about this. So QB will be 0 equal to L0. So if QBS is 0, right? And suppose L0 on S is H on S. Okay, then QB with 1 over, let me see what. Yeah. So QB on S. Sorry, QB B0S, right, is QB B0S because QB on S is 0, right? Yeah, which is L0S, which is HS. Right? So S is 1 over H times QB B0S. Okay, so any state which is L0 not equal to 0 and which is QB invariant can be removed from cohomology. Yeah, so none of these will be in a cubic homology. Okay, anyway, so let's leave this aside for now and we'll come back to this, right? So let's now recall one more thing that we had encountered for the bosonic string theory, which is that if you recall the physical vertex operators, they are contained as C ghost. Okay, they're the vertex operator bosonic string theory vertex operators. Here are form C of Z, C tilde of Z, V of Z, Z. What? Okay, at least represented as which is chosen this way. Okay. And we had given a physical interpretation of why we have this C and C tilde. Okay. And that is the following, that if we have a vertex operator inserted at a point, right, then that's a marked point on the Riemann surface. And the way we had introduced Riemann surface with marked points, okay, is that we take all possible metric and you mod out by the diffeomorphism, okay, because those are gauge transformations, which vanish at the location of those marked points. Okay, this was the moduli space of Riemann surface with n marked points. Okay. And the fact that you are restricting the diffeomorphism to vanish at those points, okay, means that the moduli space has more dimension than it would normally have if you didn't require the diffeomorphism to vanish at those points. Because vanishing at those points restricts the possible diffeomorphisms, right? Which is what you are quotienting by. So if what you are quotienting by is a smaller group, right, because you have restricted the diffeomorphisms to vanish at those points, then the actual space will be bigger, right? Because it's a set of all possible metric on the Riemann surface modded out by those diffeomorphisms.
So like the finite number of points, I mean, the diffeomorphism groups is, I mean, way high, way bigger than the, how do I say this?
Yeah, it's an infinite dimensional group, but the metric space is also infinite dimensional, right? And you are taking the quotient by the diffeomorphism and while.
In terms of the counting won't change, right?
Counting won't change.
Right, but for example, number of independent generators of the remaining.
No, generators will not change, but as a group, yeah, and the group will be a little lower dimension, right? It's infinity minus 2. But the important point is that the quotient is a finite dimensional space, right? And there it makes a difference. Because the moduli space of Riemann surface is a finite dimensional group. Now if you fix some points and say the diffeomorphisms are not allowed to be non-zero at those, have to vanish at those points, right? Then you are changing the quotient group by a certain amount, and hence the moduli space dimension will go up, right? And if you recall when we introduce interactions, right, the way you parameterize the moduli space is by requiring the diffeomorphisms vanish at those points. Okay. And this presence of C basically what it guarantees is that if you have another C, okay, then that C vanishes at the location of the punctures. Okay. And why is that important? Because that C, I mean, we say the C's are in one-to-one correspondence with the diffeomorphism parameters, right? That's the way you introduce the ghosts in the first place, C ghosts, right? So C ghosts should be required from physical principle. C ghosts should vanish at the location of the vertex operators, okay? And that's why we need the C at the location of the vertex operator. Is this clear? Yeah, that was the physical reasoning we had given as to why the vertex operator should be accompanied by the C and C tilde.
If you say this, it's very general. If you have a theory with some invariance, let's say diffeomorphism invariance, and you want to obtain a theory in which the theory is diffeomorphism invariant, but diffeomorphism does not act on certain points.
Exactly.
And you can always construct a ghost, and which multiplies with these vertex operators, as that, I mean, because C is 0.
Yeah, so the ghost field, so that means the ghost field that you introduce should be restricted field, which should vanish at those points, right? And having the C's there essentially guarantees that, right? Otherwise, you have to say, okay, if you remove the C's, but then the ghost should be forced to vanish there, right? So instead of that, so that will not be, so then the action will have to have those as constraints, right? Yeah, so having this C here, right, and the fact that C is Grassmann odd does that job, right? Which otherwise you have to impose by hand. You have to say the C is a field which is forced to vanish at those points. Right? That would do the job equally well, but that's something that you have to specify, right? Equivalently, we can say that you just introduce this CC tilde.
The ghost field to vanish at those fields at the mark points?
Because the ghost fields are in one-to-one correspondence with the gauge transformation parameters, right? And the gauge transformation parameters we said have to vanish at those points. So the ghost fields have to vanish at those points. Take another C of W, right? In the correlation function, right? Whenever W goes close to Z, it vanishes, right? The correlation function. That's equivalent to saying the C of W vanishes at those points. W is the fourth one. Yeah. Okay, now we are going to try to generalize this to the vortex operators in the Fermionic string theory. Okay. So for as far as the diffeomorphism ghosts are concerned, it's the same argument. They have to vanish at the locations of vortex operators. So you should have CC tilde. But now you also want to demand that the superconformal ghosts should also vanish, right? The gamma, because we want to make sure the supersymmetric transformation parameters should also have a 0 at those points. Yeah, so gammas are not Grassmann, right? So by following the logic, we should require that gammas should vanish at the vortex operator. But the problem is that to achieve this, we cannot use gamma or beta because gamma is non-singular. It's finite as Z goes to W. And gamma W beta Z, of course, is infinite, right? So while we know what we want to do, we are not able to achieve this just by attaching some gammas in the vortex operator. Is this clear? So what we need, vortex operators of the form delta gamma is just Dirac delta, but with gamma as an argument, right? Gamma of Z. Gamma of W, delta gamma of Z should go to 0 as W goes to Z. Right? Because as W goes to Z, gamma of W goes to gamma of Z, and X gamma X is always 0. X delta X. Some new operator. No. It's a Dirac delta function with argument gamma of Z.
It should be defined in the function integral somehow. By saying that the function integral of this is just some.
Yeah. You can see it that way. You can say it that way. Yeah.
Delta of gamma is a Dirac delta of gamma.
Yeah.
Meaning?
Delta of X, you know, right?
Yeah.
So take the delta of x, right? Given any function of x, right? We can replace that x by the field, right? Sine of x is a function. Sine of phi of x is just take the value of phi of x and calculate sine of that, right? So I'm saying delta of x is not a function, it's a distribution. You can think of the limit of a function. Pardon? Yeah, that can serve as a definition, but I'm saying that you can give various representations, right? But delta gamma of z is, you take delta of x, okay, regard this as a limit of a function, and inside x, you put gamma of z.
Should it be thought of an operator in the same?
It should be.
Should.
Hmm.
So it will have OP, it will have.
Well, this is OP with gamma. Pardon?
There are mode expansion.
We'll see what it has, right?
Like, for example, data function can be written in terms of some of mode.
If I know OP of delta gamma with delta, I'm done.
There is a representation there.
Yeah, roughly, yeah. And it will have a singularity, 1 over z minus w, because OP of delta gamma with beta will be delta prime gamma times 1 over z minus w. Because if beta of z with gamma of w has 1 over z minus w, then OP will have that structure, derivative, right?
There's some hidden field.
Yeah, so you are not going to unhide them, right?
Okay.
Those hidden fields. Okay, so the point is one could start this way, right? We could start by saying that we introduce delta gamma and delta beta as some fields, okay, and try to find their OP, etc., right? But what I'll do is I'll give a equivalent description of the beta gamma system, right, where the role of delta gamma and delta beta will become clear, right? What these operators are. Okay. So let me write down an equivalent description of the beta gamma system. It's equivalent in the sense of CFT. And this is a pair of fermions xi eta and a scalar phi.
Really something like a condition of satisfying that delta condition. I mean, the delta is probably, I mean, I'm thinking of the delta as some integral representation or some other field imposing the fact that gamma of z.
You can think of it that way because delta x has various representations, right? Integral dk to the I k dot x dx, right? So you take the representation and replace x by gamma of z, and you can define it that way, but it's a somewhat inconvenient way to define it, right? But this will make it explicitly clear that it's a local operator. So let me give the OPs. So xi eta is a usual pair. Xi of z, eta of w is 1 over z minus w. Okay. And phi, I'll write as del phi of z, del phi of w is minus 1 over z minus w square. So this is like the usual scalar field on a pair of fermions. Okay, xi eta has 1 over z. This is like a BC system or the psi system, right? Psi bar system. This is similar to a pair of fermions. This is like a scalar, right? Up to a normalization, there are some alpha prime over truth which I have removed. But the reason that this is not a normal system, right? Normal fermion or normal scalar, okay, is hidden in the form of the energy momentum tensor. Okay, so let me give the form of the energy momentum tensor.
beta gamma host energy momentum tensor in terms of its psi eta?
Yeah. Okay. So T is I eta, I'll write. So T of the xi eta system is given by
It factorizes between psi eta and phi.
well, on the sphere it factorizes, but on higher genus surface it doesn't factorize. The fact that you are thinking of this as two independent system is somewhat of an illusion, right? It on the sphere or on the plane when you calculate correlation functions it does factorize, okay, but not on higher genus surface. The correlation functions. See, this correlation function of psi eta phi, right? Take arbitrary set of psi eta and e to the phi. Okay. That correlation function you can write as a psi eta correlation function times, yeah, phi is independent of psi eta.
Beta gamma, I thought is a full expression that is dependent on psi eta and phi. Yeah, but you're writing separately.
I'll write separately because these are on the sphere this can really be thought of as independent field. So T phi is minus half
What does it have to do with the topology? I mean, this is a local field. T phi and
yeah, this is a local field, but if xi eta and phi had been different fields, genuinely different fields, right? Suppose there is an action which you can write as xi eta action and a phi action, right? Then on any higher genus surface, when you calculate a correlation function, you can separately calculate the correlation function of the xi eta system and the correlation of the phi system, right? So suppose xi etas are placed at some points yi and zi, and phi's are placed at some wi's, right? Then it will be a function of yi zi times a function of the wi's, right? For a decoupled system. But that doesn't happen. Higher genus correlation functions couple wi's and zi's and yi's in a non-trivial fashion.
but T is still like this should be exactly.
Yeah, T is still this, right? They're separate T's, but the actual correlation functions of xi eta phi system doesn't factorize. How do I get these things? Yeah, so I'll tell you how the various consistency conditions, right? So you from this we can check that C of xi eta is -2 and C of phi is 13. Okay, just have to calculate T xi eta, right? All the things are given. Okay. This exercise. So T of xi eta plus T of phi is T of beta gamma. Sorry, C. Right? If you remember, this was 11. Okay, this is the first check that the central charge of the xi eta phi system is the same as the central charge of the beta gamma system. Pardon? Free scalar, yeah. Yeah. So on the plane, there is no subtlety. Free scalar and free fermion, right? The only unusual thing is the structure of the energy. No, there's a del square phi, which you don't have normally, right?
Get this from a Lagrange.
You can. You have to couple this worldsheet R. Yeah. Yeah, phi. If you have phi R, right, and then vary them with that to the pseudometric, you get term proportional del square phi.
The BRC action.
Gauge fixed action, yeah.
Fixed action. And there is there some expression? I mean, there should probably be some expression of beta gamma in terms of psi eta and phi, which I can put it there and then phi.
No, it's not. There's a local redefinition like that. Right? It's like bosonization doesn't have a very clear local thing, and you cannot substitute in Lagrangian and get back the original, the other Lagrangian, right? This is at a quantum equivalence. The equivalence at a quantum level, right? Not at the level of classical action. That you cannot simply say that you write beta in terms of xi eta phi and gamma in terms of xi eta phi, and a classical beta gamma action will become the classical xi eta phi action. I'm going to give the dictionary. Yeah, I'll give the dictionary. No, but that dictionary is quantum. I mean, operator translation, right?
What operator should I measure in beta gamma system?
Yes.
What operator I should measure?
Yeah, I'll give you that dictionary. I'll give you the dictionary, but for that, we have to learn a little more. Right? The conformal weights, for example.
This is not enough. Matching of C. We could have had.
Yeah, this is not enough. You have to make sure that everything. Yeah, I agree. So this is not enough. That you have to do more. Why are you doing this? We will see why. We have to find the delta gamma and delta beta, no? So we'll find the delta gamma and delta beta in this language. Okay, so exercise. Xi has weight. Yeah, 0, 0.
We are only on the right sector, right?
Yeah.
Is that still true?
Yeah, it's still true.
So this scalar will have that chiral problem.
Yeah. So then we are not trying to write a Lagrangian for this.
But we have a chiral scalar.
Yeah, chiral scalar. Yeah. There are problems in writing a Lagrangian, right?
As an abstract CFT, it's fine.
As an abstract CFT, you have to be careful. You have to make sure that everything is okay with modular inference, etc. Okay. But so this is a consistent theory. It's a redefinition of a rewriting of the beta gamma system.
The beta gamma way of looking at superstrings is not the correct way, and that you should probably start. Is it not possible to start directly from xi beta phi?
It's not clear directly on by gauge fixing, right? You get beta gamma.
That's by
Gauge fixing, I mean, standard supercoast gauge fixing, supersymmetric gauge fixing will give beta gamma. Right? And it's only at the level of the CFT. See, because there you are thinking in the semi-classical language, right? We write an action, we gauge fix, we get the beta gamma as a host. Okay? This translation from beta gamma to xi eta phi, okay, is a result in quantum conformal field theory.
Yeah, something of the sort of is there a classical action which upon gauge fixing will give you xi eta and phi instead of beta gamma?
As a host. So I don't know of any way to do that. Right? And there is a reason for this, right? The psi eta phi system is a little bigger than the beta gamma system, which also I'll discuss, right? It's not every operator in psi eta phi system will be allowed. Okay, so this is clear. Xi has weight 0, 0, eta has weight 0, 1. Okay. The e to the q phi okay, this I'll do. Let me try to do this. These things are straightforward, right? Just take t xi eta and calculate the OP with xi. Right? We have already given the xi eta OP. So from that you can check that this is true.
You can change it. I mean, I put the total derivative down in B.
Yeah, but the total derivative is important, right? So xi and eta are not symmetric. Because total derivative, you're not doing integral. It's true. Integral of t doesn't care, right? Whether you put the derivative one or the other. But this requires actually local t xi eta. Right? And that's why there's a difference between xi and eta. Okay, so from this one, it follows that del phi with e to the qw, del phi of z to the qw, u phi of w. Pardon?
Just we need the phi.
I have given here. Well, you can work on phi from there. Yeah, except the phi is not a conformal field, so I didn't write it that way. E to the q phi is. No, it's not a primary. So it's a good field. Del phi is a good field.
So does what it?
Yeah, you can.
This is
Yeah, holomorphic only. Yeah, del phi is a good CFT, good operator. Right? Del phi and e to the q phi are good operators. It's just phi is a problematic, right? Because phi OP is a log. You can just integrate it twice and you can see, right?
Going with the analogy of vertex operators of the x's, we write e to the ikx instead of
Yeah.
kx.
Yeah. So here we are not writing e to the ikx because this q's will be real. Yeah, if we just take the derivative, I mean, to check this by taking del w on both sides, and take q to 0. Yeah, that's one way to test this, because if you take the del w, it will bring out a q del phi times e to the q phi. On this side, if you take del w, the leading term will come from here, right? By taking the derivative, and then the q's will cancel, and then if we just remove the q to the q phi part, you recover this. And e to the q1 phi of z, e to the q2 phi of w is z minus w to the power minus q1 q2. Okay, again, to test this, you can just take the derivative of yeah. So once you have accepted this, you take the derivative with respect to z, right, and check that agrees with this. Yeah.
If you take del w on the right, you also have on the e to the q phi.
Here.
On the right also.
Yeah, that is less singular. Right? The leading singular term, 1 over z minus w squared part, comes from taking derivative on this. Right?
So the other thing is not even there.
Yeah, so other thing will be less singular. Yeah, there will be dot everywhere, yeah. Everywhere, yeah. Subleading terms. Yeah, I'm only writing the leading terms. Yeah, subleading regular is also subleading, right? Meaning subleading compared to whatever term I have written.
He's saying in the OP, right, all nonce.
Yeah, I agree. Yeah, yeah. So regular, because if you start with 1 over z minus w, then it will be regular terms.
Or at least for Q1, Q2, say positive, Q1, Q2 greater than 0.
Hmm.
I mean, it seems like there is only just one singular term.
Here?
No matter what Q1.
Here. No, there will be term proportional to e to the q1 plus q2 phi del phi, right? With one less power. Then del square phi with one less power and so on, right? Those should be, but those will be less power.
Yeah, then they will be singular.
They'll be singular, depending on q1 and q2 values, right?
That can be subleading singular.
Yeah, there can be in this, there can be subleading singular term. In this, there cannot be because The leading one is 1 over z minus 1.
You write all singular terms explicitly, right?
Not necessarily.
Because
Okay, it depends on what you want to do. I've just only given the leading term. Right?
Whether we can write or.
You can in principle write. Yeah, you can write. Yeah, you can just have to do Taylor expansion. You can work at all the subleading singular terms. So from this, we can also calculate T phi of z e to the q phi of w. And this is given by minus half q square minus q So this minus half q square you can recognize. That basically comes from this term with e to the q phi, right? This is the same reason why e to the I k dot x has this type of conformal over alpha prime k square by 4, right? It's the same term. Pardon? Yeah, except but here the normalization is slightly different, right? Here there's no 1 over 2. For the x, there is a alpha prime over 2 or something, right? That's why you got x k square by 4. Here we are getting 1 over 2. This minus sign comes because it's e to the q phi instead of I q phi. This minus q is because of this term. It's 2 del square phi. When you take the OP, right? Del phi with e to the q phi will bring down minus q over z minus w. And the next time you take a derivative, right? The leading term will come from derivative of this. And that's what gives you minus q. Okay. So conformal weight of e to the q phi is this clear? What will be? Oh, in this case, the 1 over z minus w times the derivative of this. Okay. That part is always fixed because it's L minus 1.
we need that to argue that e to the q phi is a primary.
Well, if it's not a primary, there will be no more singular terms, right? That term you cannot change. In general, there may be, but that the 1 over z minus w, that is always derivative of the operator. L minus 1, right? L minus 1 always generates derivative. So now I'll give the translation. Translation. So beta is going to be del xi e to the minus phi. Gamma is beta e to the phi.
But you said these are global.
What? No, I'm changing. You cannot use this and substitute in the action to recover the action for xi eta phi. This is a quantum field definition, not classical field definition.
With the 1p effect, right?
The full 1pi effective action. I mean, we don't even do 1pi effective action in the world theory like this, right? So this is, so the statement is that the correlation functions of these operators, right? If you calculate the beta gamma correlation function on the plane can be calculated by using the correlation functions of these on the plane. How do you do that? Meaning?
How did you know that?
How did I know this? I have to check. So I'll check various consistency conditions, right? Oh, I didn't guess it. Frida and Martinek Shankar guessed it, right? And Frida and Martinek Shankar, there's a in mid 80s. I mean, if anybody could guess it, then they wouldn't have written a paper on it, right? So the very fact that they have written a paper on it means that you cannot guess it. At least not in a straightforward way, right? You have to, I mean, do various checks. But I'll tell you what how the definition of at least the various fields in terms of beta and gamma, right? The reverse definition. I'm now giving the beta and gamma in terms of these fields, right? Now I should also give the xi, eta, phi in terms of beta and gamma, right? That I'll do that, and that will become clear in a minute. Okay. So delta beta in this language is e to the phi, and delta gamma is e to the minus phi. What?
Certainly depends.
Pardon? I'm giving the translation, right? The various operators from the beta gamma system to the xi eta phi system. Pardon?
There are no xi and eta on the right hand side.
No xi eta on the right hand side. Either e to the phi and e to the minus phi.
To get correct vertex factors, we only need delta functions of beta and gamma, right?
Yeah, so now you're only need 5.
We only need 5.
Yeah.
So why do we need actually the pair of fermions in him? I mean, as long as we.
Other operators.
The point we started with the beta gamma, right? So yeah, just like we said, we have to put a C. You could have asked why do you need B, right? On B are needed for other things.
Is this choice because if I just go through with central charge argument, I could take
do many other things. I agree. Yeah. With that you can do many things, right? So the correct way to proceed, right, will be to use these as a definition of phi. Okay?
Yes.
Delta beta we can define phi to delta beta is e to the phi and delta gamma is e to the minus phi. How will I'll check? We'll check this. Right? It has to have the correct properties, right? First, let's take the conformal weights. Right? That's the first thing we should check. Okay? So H beta should be equal to H of del xi plus H of e to the minus phi, right? So let's just check that. So this is H of del xi is 1, right? I'm not counting the left moving because that's always 0, right? Xi is dimension 0. Dimension I gave. Yeah, because here, right? Yeah, del xi is dimension 1. If you have dimension 0 primary, you can check that it del xi is dimension 1 primary.
And this will give you -1.
Yeah, so e to the minus phi, right, has what dimension? So q is -1, right? So here it's -12 and then +1, right? That is 3/2. So H beta has the correct conformal weight. So H gamma is H eta plus H e to the phi. Eta has dimension 1 and e to the phi we'll have this is again -12 and this is -1. So that's -12. Eta has dimension 1. Yeah. Here. Eta has weight 0, 1. Right, yeah. Left is always 0. So you don't worry about the right left. Is this clear?
Would this constrain this form? These two should constrain this form quite a bit, right? Like just by saying that H beta as a function of H psi and H e to the minus phi. And then H gamma has to be a function of, all three. Psi,
yeah, but the point is you can change various things, right? So, okay, central charges have to add up and the beta gamma conformal weights have to add up. Okay? But you could change, for example, these powers here. Right? There are things we can, play around with. Yeah, at least it doesn't look like a unique choice, but let me give you the reverse definition. So then it will become clear. But first, let's check the other properties, right? This property, gamma of W, delta gamma of Z should be 0, right? So let's check what that is, right? Gamma of Z, gamma of W, delta gamma of Z, right? So that's, according to this, eta e to the phi of W, and delta gamma of Z is e to the minus phi of Z, right? So this OP is W minus Z, right? Minus Q1, Q2, so plus 1. So this is W minus Z, eta of Z, plus. So it goes to 0 as W goes to 0. Pardon? Yeah, others are perfectly regular, but it vanishes at W equal to Z. These are not these are hard powers of W minus Z, right? These are leading powers. So these are W minus Z square or higher. Is this clear? Why are people looking confused?
No, I mean, the
No?
argument is that we can, I mean, I think you are going to reverse engineer it, like, if we start from here, gamma W, that's the starting point, say.
Yeah, so let me do the next one, then it will be, then I'll reverse, right? Let's do the beta, right? Beta of W, delta beta of Z. That is del xi e to the minus phi of W e to the phi of Z, and that is basically W minus Z del xi of Z plus higher order terms. So again, it vanishes as W goes to Z. Pardon? Well, no, a beta times delta beta should be should have a 0, right? We don't need it, but I mean, I'm saying that this should hold, right? What? Many operators may do the job. I agree. We'll come to, as I said, I'll give the reverse. I have to give xi eta phi in terms of beta and gamma, right? Then everything will be unique. That will be the inverse of this relation. Yeah, okay. So this is clear, right? At least these OPs are working out correctly. And the final one that I didn't say, that also is easy to check. Beta of Z, gamma of W, you can check is 1 over Z minus W plus non-singular. Right? You have to calculate the OP of this with this. Right? And the only thing you have to be careful about is e to the plus minus phi, these are Grassmann odd. Okay, even though phi is Grassmann even, e to the plus minus phi is Grassmann odd, and that one way to see this is that its conformal weight of e to the plus minus phi is half integral. Right? You can see this minus half or half, right? Half integral weight objects are Grassmann odd typically, right? Because their OP has a Z minus W. So these are Grassmann odd, and that basically means that this e to the minus phi, when you pass it through eta, it will become a minus sign. Okay, once you take into account the minus sign, you will get exactly this. Grassmann odd, right? Yeah, so when you pass e to the phi through xi, you'll get an extra minus sign. Yeah.
And then you have to do the del xi.
Yeah, then you have to go to del xi u theta. That will give you a minus 1 over Z minus W square, right? To the derivative with respect to Z. Right? So minus 1 over Z minus W square. And then that will give a minus of Z minus W, because e to the minus phi to the phi OP will give a Z minus W. So you'll get a 1 over Z minus W.
That was kind of like but I thought because it's a product of two things and you need Grassmann even in the end. And one is obviously Grassmann also.
Yeah, yeah. So other one has to be Grassmann odd. And that's another way of saying it. Yeah. Yeah, exactly. Okay, so now let me give the reverse, right? How can we define phi xi eta in terms of beta and gamma? Okay. and it's basically the reverse of that relation. So you define e to the phi as delta beta. E to the minus phi as delta gamma. Then you define eta as limit w goes to z 1 over w minus z gamma of w delta gamma of z. Because you know that gamma of w delta gamma of z should have a 0, right? So the coefficient of that 0 you declare as eta. Is that clear? And then you declare del xi as limit of w goes to z 1 over w minus z beta of w delta beta of z.
Whether it should go like there, gamma delta gamma has to go to 0 in linear fashion. It could have gone in quadratic fashion.
Then eta will be 0.
Yeah, I mean, eta looks like, I mean, I don't know what you call it, the
Yeah.
rate at which it is going 0.
Yeah. So the point is, if it had gone to quadratic fashion, you can show there will be inconsistency because you cannot declare eta to be 0, right? And get a consistent theory because then the central charges will not match up.
So I guess then it would be like you start with this, and then can I eventually find?
Yeah, you can find all the properties of the phi eta psi system from these definitions.
What is the gamma delta?
Gamma, you can work out now. Gamma delta beta. But yeah, once you have made this identification, right?
Gamma and delta.
But you can find from here. Gamma with delta beta, right? It will have a pole. E to the phi is e to the phi. Yeah. So now you can find everything, right? Once you have given this dictionary, right, from beta gamma to xi eta phi, you can use xi eta phi system, right, and calculate the OPU, arbitrary set of gammas, arbitrary set of betas, and delta gammas and delta betas.
Within the beta gamma system. See, in this language, I can find gamma delta beta OP or beta gamma delta gamma OP.
Yeah.
And I'll get something in terms of beta and xi. You can rewrite it in theta gamma in principle.
Theta gamma. Xi is like theta gamma, but you see from. Pardon?
I'm saying I want the beta delta gamma OP in the beta gamma language.
No, in the beta gamma language you will not get. In the beta gamma language, you see, you will get in terms of eta. Here, beta gamma with delta beta you what you want, right? You will get eta e to the 2 phi. Right?
It's not easy to invert.
It's not easy to invert, right? Eta, you know, it is this, and e to the 2 phi will be like delta beta square, right? With some, I mean, you have to separate out some z minus w parts, right? Because e to the phi with e to the phi, OP will have the leading term as e to the 2 phi, but with the coefficient 1 over z minus w.
So operator in the xi eta phi system.
Yes.
Delta beta square does not send some like.
No, delta beta square, so you have to define this as OP. Delta beta of z times delta beta of w. In the z goes to w limit, right? And divide by 1 over z minus w, or multiply by 1 over z minus w, right? That is, yeah, is well defined. Okay. So as I said, you could take these as the definitions, okay, and work out the properties of the beta gamma, the eta xi beta system, yes, eta xi phi system, in terms of the properties of the beta gamma system. Okay. But this is not a classical equivalence. Right? This tells you how to calculate the correlation functions of the xi eta phi system in terms of the beta gamma system.
if you take BC closed system, I mean, the exponential we can still define, right? This exponential equation with the BC.
Yeah,
Not
yeah, you can define.
But then the fermionic counter
Are not there.
The scalar, the bosonic counterpart of it, zeta and delta zeta, won't be a limit. Just they would be very.
They are just not there. Yeah, because it's an identity, right?
You think this is identity?
So the zeta system will not be there. But you are indeed right. You can write V as e to the phi and C as e to the minus phi, right? And that phi will have a different k, right, in the expression of energy momentum tensor. So the central charge is 26. And you can rewrite things that way. Okay, but that will be a more trivial kind of change of variable. Okay. Now, the non-trivial part, as I said, is you see this provides a definition of eta and del xi, but not xi itself. Okay. So this suggests that when you want to translate operators from the beta gamma system to the xi eta phi system, you should not include any operator where xi doesn't have a derivative. Okay. So the only operator that you should consider in the xi eta phi system where every factor of xi comes with at least one derivative. Is this clear?
Just not a statement of fact. Xi has 0, 0, 1, so anyway we shouldn't expect it to be a good operator.
No, it's not that statement because not every 0, 0, this is a 0, 0 fermion, and 0, 0 fermions are perfectly good operators.
Yeah.
Yeah.
So any operator except the identity in the CFT should not have 0.
This is a non-unitary theory, right? You can have, yeah. Yeah, e to the I k dot x for k square equal to 0 has dimension 0, right? It's perfectly good operator. So that is not the reason, right? The reason is that if when you translate from beta gamma to this system, the xi always comes with a derivative. Right? So this means that you shouldn't include del xi as in part of your operator. When you try to list all the possible operators in the xi eta phi system, right? You can make a one-to-one correspondence between the operators in the xi eta phi system and the operators in the beta gamma system, provided you leave out any operator that has xi without derivative.
Those operators are well defined from the xi eta.
Yeah, they are well defined from the xi eta phi system, but not beta gamma system. Okay. So using the state operator correspondence, right, this translates to a statement on the states, right? What kind of states in the Hilbert space would you allow, right? And the point is in terms of Hilbert space states, do not allow xi 0 oscillator. Okay. So the point is xi 0 on the vacuum is not 0. So you could in principle create states by applying xi 0. Okay. But the corresponding operator, vortex operator, will have a xi without derivative. Okay. So the statement is that you shouldn't allow states in the Hilbert space which have xi 0 oscillator acting on the vacuum. Okay. This is what is called a small Hilbert space.
By not.
Yeah, by not allowing. Yeah. Okay, now let me define picture number. Okay, so host number E and beta are -1, C and gamma are 1. Okay, this is standard. In the xi eta phi system, we will use xi as -1, eta as 1, and e to the q phi as 0. Okay, then you see that it with this the host number assignment is correct. Del xi e to the minus phi will have host number -1, and eta e to the phi will have host number 1.
So the seek host number conservation is separate from the beta gamma host conservation.
Well, a priori at the level of the correlation functions, but we will see that eventually what matters is the total host number. So B and beta we are assigning both host number -1. Because QB mixes them up. Right? Because you remember QB has a gamma square B, right? It has a C TM, right, which has a C host number as extra C, and there's a gamma square B, right? So those two don't have separate the BC and beta gamma host number, right? The total host number is 1 of QB, but you have to count both of these.
TF has some host.
TF, no, TF doesn't have a host number because it's gamma B.
Different terms of different host number.
No, TF doesn't have a host number. Gamma has a host number. Gamma square B. Gamma TF and gamma square B. Yeah, JB has host number 1. Yeah, JB has host number 1.
And since JB is either C times something or gamma times something,
Yeah.
all the T's are host number C.
Yeah, exactly. Okay, now there is also another quantity called picture number, which arises only after you use this xi eta phi description. Okay. So picture number is B, C, beta, gamma are all 0. E to the q phi has q, xi has 1, beta has -1.
Number is the U1, is some U1 in the action.
Yeah,
Picture number is also some U1.
yeah, it's some U1, right? But that U1 is not visible in the beta gamma system. Beta and gamma are all neutral under the U1, right? But once you include the phi, because you see the way you have assigned, right? Beta and gamma are neutral, right? It has arisen only because of this fact that you have splitting up del xi and to the minus phi, right? So the picture number is essentially counting how many delta gammas you have and how many delta betas. That is the difference between the two. Because delta gamma, see delta gamma is e to the minus phi, right? So every delta gamma has a picture number -1. Okay? And the point is that delta gammas, you can say, you might think that gamma times delta gamma should cancel out, right? But it doesn't cancel out. Okay, gamma has a 0 at the location of delta gamma, but gamma times delta gamma is not an identity, right? It's not z minus w times identity. So how many times you have delta gamma, right? That's a conserved quantity. How many times you have delta gamma minus how many times you have delta. Picture number -1.
If it is like a global conserved charge, then we can show that some conserved current.
You can write, yeah. You can write.
It's a global charge of the one.
Yeah. So the conserved current is del phi on the phi and then xi eta, right? Some linear combination of del phi and xi eta. Right? But it's just in the terms of beta gamma, it's 0. There is no local expression in terms of beta gamma. So picture number is something which is counting the number of times delta gamma has appeared in the correlation function minus number of times delta beta has appeared in the correlation function.
We didn't try any action for these. We don't need it, or we can we write it?
We can write it, but the action is not very useful. Action is again xi del bar eta, right?
There, but it is clear to see that correct.
Yeah. So if you write action is a free scalar field and free xi eta, right?
Can't go from beta gamma to
No, not that way. But I'm saying formally you can just write an action. Right? For scalar field, it's a little more complicated. Right? For xi eta, integral xi del bar eta, you can write. It's a busy ghost system.
But then the interaction terms of the psi eta you don't.
No, they're a free field. Psi eta and phi are free field. Right? All the correlation functions have been calculated thinking of them as free fields. Right? But as I said, they are free fields only on the plane. On higher genus surface, they have non-trivial correlation, right? It's not really genuinely free field.
So is that at the level of action, since phi and psi eta systems are decoupled, you would have thought there are two conserved charges.
Yeah, true.
At the level of interactions, there are not.
QB doesn't conserve those, right? QB can mix them up. So two conserved currents for the phi eta I system, you can say yes, ghost number and this one, picture number, right? Those are the two. No. If you forget about the beta gamma, PC are decoupled anyway, right? Let's just think of xi eta phi system. There are two conserved currents, right? As you said, xi eta and del phi. Those are the ghost number and picture number.
Okay, that is the.
Right? Those are the two.
You could have constructed a current which does not do anything to zeta eta.
Yeah, you can construct. Just take the sum of these two. Right?
That's a well-defined number.
Just a well-defined number, it will do something to phi. Yeah. Okay, so maybe next time we'll continue on with this, right? So you have to now build states in each picture number separately, right? And we'll see what their properties are.
There is a delta gamma.
Eta has a delta gamma.
Picture number I can say is 1.
Yeah, delta gamma is -1. Yeah, delta gamma is. We have defined that way, right? E to the -5 has -1.
Picture number is like number of delta.
Number of delta beta minus number of delta. Is that right? Yeah. Number of delta beta minus number of delta.
Delta beta is plus.
Delta beta is, yeah, e to the +5, exactly.
But it has nothing to do with the physical state.
No.
In each ghost number sector, you can find physical state.
Yeah, but now what you are saying is that from the physical argument that we gave, like just like the C should accompany a vortex operator, we can say delta gamma, right, which is e to the -5, should accompany a vortex operator. Right? So that will be what we call the canonical picture vortex operator. Okay, e to the -5. No. We'll mode expand everything else on top of e to the -5. E to the -5 is e to the ik dot x, right? That is not mode expand. Right? You create a fog vacuum carrying momentum k. Yeah. So here similarly here q will be just the analog playing the analog of that k, role of k. Yes, you write a status k comma q and mode expand everything in that on that.
With the assumption that q is already minus.
Not necessarily. We'll do it for every q. Right? But as I say, q equal to -1 is special because that's what is called a canonical picture number.
That is supposed to give us physical state.
That is supposed to give us physical states.
One thing you have been saying that on higher genus, these will break down somehow. Won't give us the correlator.
Yeah, I mean, we know exactly what the correlators are on higher genus surfaces.
Is it because it will take some phase or
Yeah, it's related to that, right? It's just that these are, the fact that these are decoupled, right, is only a myth, that they are decoupled on the plane.
so I mean, it will go around the cycle and eta will somehow become phi.
No, not eta will become phi. The actual correlation function will have a function, will be a function which depends on the argument of eta and argument of phi in a non-trivial way, not as a product. Right? Because if you have two decoupled system, right? Say you are calculating the thing on the torus, then there will be a separate correlation function on the torus for the first system and times of the second system, right? That will not happen in this case.
Story about plumbing picture where you, like when you were doing in last course 2D CFT, you were saying that higher genus things we can find out by the real correlation.
Plumbing fixture will work fine. In the plumbing fixture limit, it will factorize.
Exact statement.
No, no. Plumbing picture is you have to do the expansion in powers of this Q, no? You take ZW equal to Q, and in the Q goes to zero limit,
Yeah.
you factorize.
No, no, I'm not yeah, saying the wrong one. I mean, when you started saying that higher genus things, we can just think of them.
Okay,
as
glue.
having
Yeah,
that
yeah, yeah.
gluing,
Yeah.
not-
Yeah,
gluing,
fine, yeah.
gluing is a-
Yeah,
So this gluing picture. So everything you can boil down to sphere correlation.
exactly. Yeah,
Which do fact.
yeah.
But the intermediate steps are mixing.
The gluing, after gluing, it will not factorize. It's a strange fact, but it's fact. It's true.
This is not true for any generic CFT. I can just write down two decoupled CFTs on the plate and start doing the procedure on torus, and I'll expect still decoupled.
Yeah, but in this case, it will not decouple because of the fact that various conservation laws are non-trivial. Okay? The host number conservation, etc., non-trivial. Right? You have to introduce some appropriate picture name changing operators and so on, and that will make it not factorize. But plumbing picture is still true.
The procedure is still the same.
Yeah, procedure is still the same.
The fact that these are two CFTs.
Yeah.
Is it a very non-trivial statement that after all this blah blah, something unitary pops out?
Unitary, what pops out? Unitary.
Final correlation.
Yeah, they will be unitary.
But that's a very non-trivial because at each intermediate step we have blah blah.
True, yeah. I mean, it's the fact that I mean, you have to check that in the BRST cohomology, right? You can choose representatives which are manifestly positive norm, right? And that the pure gauge states decouple from the correlation function, right? Those are the two things you have to check.
But in the Zeta system, there's no. Okay, I don't know that analog because gauge transformation, the diffeomorphism transformation parameters are linked with gamma.
Yeah, but these are worldsheet diffeomorphism. Now you are talking about the QB, right? Will be space-time viewpoint.
Exact states.
QB exact states decouple. Right? That is something that you can prove at the level of the correlation functions. At the level, yeah, and that we'll discuss, right? And,
In terms of psi and phi.
yeah, that you can do
By substitution.
by substitution.
That's when Godwin was asking that this does not, why does this not work for action? You're saying it can work for.
For QB, it's fine. Yeah, QB is an operator, right? I mean, these are operator statements, right? So when you write JB as gamma square B, right? Yeah, you can replace gamma by this, exactly. Yeah, because gamma square is non-singular, right? So it better be that the gamma square calculated from here is non-singular, right? And it is in a non-singular. Because e to the 5 with e to the 5 would have a singularity, but eta with eta would have a 0, right? So gamma square is basically del eta times e to the 2 pi. That operator, right? With up to a sign. Del eta e to the 2 phi, right? Yeah, eta of z e to the phi of z, eta of w e to the phi of w, right? Yeah, so this is minus that we have to take to that side, and then you get del eta times eta and e to the 2 phi, right? This will have a z minus w, and the second e to the phi will have a z minus w inverse. Because eta square is 0, right? So you have to Taylor says expand eta. Because eta is Grassmann odd, right? So eta of z, eta of w is z minus w del eta of w. Eta of w, right? So that's why you get del eta, and this gives you e to the 2 phi. So gamma square is a well-defined operator. This will enter QB. This times B will enter QB.
Any operator I have in the system, I can rewrite it.
Yeah.
We'll mention some polynomials. So all Hilbert spaces where we do not accept these oscillators.
Yes, Xi not oscillators.
And we'll work in this.
We will work in this Hilbert space, right? So all operators that we have in the theory, right, will only involve del Xi. Equivalent to all states that we'll be dealing with will not have psi 0 acting on the vacuum. I think this should be all in Polchinski, yeah.
I think the first chapter,